and it's also here in the notes. Right there. There are two equivalent ones that are used. I mean, we could convert this index anywhere we want. We could let it start at 0, we could let it start at 8, it doesn't matter, but these are the most frequently used. You're either going to have a geometric series starting with n equals 1, there's your formula, or a geometric series starting at n equals 0.
Is it ever valuable to change the index to try to solve something?
Well, we need to change the index sometimes to work with two different series and put them together. You want their indexes to start at the same place, so you need to adjust to make them fit together. No, it's for all series. Oh, well, those formulas were for geometric. But I'm saying changing index can be for any series.
It works the same way.
Same way, yep. All right, a little bit of reading here. So far, 8.2, previous section. We can only find the actual sum of a convergent geometric series and a convergent telescopic series. Those are the only two series that we know how to find the sum of. Geometric, a convergent geometric or a convergent telescopic. Generally speaking, finding the sum of the series is very hard. So what we want is to start to establish some way of determining just if they converge or diverge. Just if they converge or diverge. All right, so first little idea here that's important before we get to this first test that we're going to talk about is, let's say I'm adding some stuff up, right? Let's say I've got this sum, I'm starting at 1, ending at never, right? And I'm adding something up. Who cares what this is? And what if I tell you that that converges, right? What if I tell you this converges? Then do you agree that if I don't start at 1, but I start at 5 instead, it should also converge? Why? Why should that also converge?
Because it only matters what it's heading to, not where it starts.
Yeah? Yes, but why, if this adds up, like if this adds up to go towards a number, why does adding up, because isn't this less stuff? Go ahead.
I would say because like, so like if you just have like A something like it's the same like kind of function. So if one converges, should the other one?
Yeah, not to the same number though, right? Not to the same answer, but they should both. So this is just what? This is A sub 1 plus A sub 2 plus A sub 3 plus A sub 4. That's what that is, right? Forever? That's what this is.
Yeah.
And I'm telling you that that adds up to a number. This is only A sub 5 plus A sub 6 plus A sub 7, right? Which is actually over here, A sub 5, A sub 6, right? So the difference between this and that is that this one's missing the first 4 of those, right? The first 4 terms. That's the only difference between these two. If that converges, if you take off 4 numbers off the front, that's not going to change the fact that this should converge also, right? So all we're doing is removing we took this out, right? We took out A1, A2, A3, A4. Those 4 that were in front, we just got rid of them, right? It should still converge. This says that if we take out a finite number of things, then the convergence stays. Yes?
Just a quick question. On the first one, if n equals 1, the other one is n equals 5.
Yeah.
Shouldn't you have to change like the subscript on the
I'm not changing the, yeah, I had a feeling someone was going to get confused with what I just did. I'm not changing the index.
Okay.
What I'm doing is I'm asking you to consider these two different sums. One of them starts at 1 and goes forever. The other one starts at 5 and goes forever. The difference between these two are just 4 terms in the beginning. And that should those 4 terms should have no impact on the convergence. If this converges, so should that. Because it's a finite number of numbers I'm taking out. And it also works with divergence, right? Like what if I tell you that this diverges? Then if I take out a finite number of things, it should still diverge. As long as it's a finite number of things I'm taking out, it should not change your convergence or divergence. That's what the second note says here, is if it diverges, then taking out a finite number of things has no impact on the sum. Yeah?
So what if the, like, let's say like the first 5 numbers, like, or I guess it's kind of hard to say. So you know how like some graphs, they have like an asymptote, like a vertical asymptote where it hits.
It would have to be defined. So these numbers, like when you plug in 1, 2, 3, 4, it would have to be defined. Like you would have to have a number.
Oh, okay.
Yeah, I mean, you couldn't have it undefined, then all bets are off. Right?
What if the asymptote is like at a decimal, so it's not on that?
That'd be okay. It wouldn't change, it would still, it would just, because it would be like hidden from us, right? We wouldn't even see it. So both of these would not, they would both miss the asymptote, right? Is that what you're saying?
Yeah.
Like if the asymptote was at 1.5, this would miss it and that would miss it. Yeah?
Well, yeah, I guess.
Yeah? Okay.
So a sequence's output can't be undefined?
Yeah, that'd be, your sequence has to be defined on the things you're plugging into it, right? For the sequence to be able to define a sequence, when you define a sequence, there, I've defined a sequence. This sequence is not defined for n equals 1, right?
Yeah.
Okay, but everywhere else it is. So if I ask you right now to find the sum, n equals 1 to infinity of n over n minus 1, I can't do this because it's not defined at 1. What I could do is start it at 2. And now I can do that.
Yeah, but then now, like, because you said that if the first,
It has to be defined. They have to be defined.
in order for those rules.
Yes,
to apply?
for the
Okay.
rules, yeah. But I told you all a while ago, the only sequences we're talking about in here are sequences that are defined over the numbers we're plugging in.
Oh, okay.
So you're bringing up special cases that I said we're not considering.
Yeah.
Yeah, that's a different scenario, which we are avoiding altogether.
I see.
All right, so now we get to our first test, all right? This is our first test on helping us try and figure out if a series converges or diverges, right? We have right now, well, do we have any tests? We have geometric series, well, n-term test, pregnancy test, right? We have that test. Geometric series, we have harmonic series, we have telescopic. Those are the things we've looked at. Now we get to the integral test, which involves integration, right? So first, a visual representation. Remember that if you see this improper integral from this class, what this improper integral means is the area underneath that function from 1 to infinity, right? So it's like, whoa, that's really big. Yeah, too big still. I have it, well, I'll get to it in a minute. It's the next one down. All right, so let's say that we've got this function, right? Defined from 1 to infinity, and let me tell you some conditions on this function. First, this function is continuous, which means it has no breaks or jumps, all right? Continuous, this is a continuous function. Also, what if I tell you that the function is positive on that interval? That means it's always above the x-axis. And then also, I tell you that the function is decreasing. That means the function is going down. Then we would have something that looks like this, right? This would be a function. It's defined from 1 to infinity. So no asymptotes, no jumps, no breaks, right? It goes down, right? And it's always above the x-axis. That would qualify as a function that satisfies those criteria? Yes? Okay. Now the test. Let's look at this particular example. I want us to look at this series right here. Look at that series. Does this converge or diverge? So let's run the nth term test, right? Ignore that, let n go to infinity, what do you get? 0. That tells you? Nothing. That's the pregnancy test. That's okay if I keep saying that? I mean, we said COVID, didn't we? COVID test?
I like pregnancy better.
Okay, whatever. Before COVID, I used pregnancy test because it made most people could associate with that. So, all right, so there we go, right? It's failed. So now, is it geometric? Is that a geometric series? No, because it's not, the n's not in the exponent. So it's not geometric. Is it harmonic? Constant over linear? No, it's not harmonic. Telescopic? Well, I don't think there's anything you can do. You can start writing terms out. You can't do partial fraction decomposition because there's no way to decompose 1 over n squared into two different things. So we don't have anything for this, all right? There's nothing we have that can figure out if this converges or diverges. But would you agree that that 1 over n squared, if I looked at it as a function, right? If I looked at this as a function, f of x, function, back in, before we started talking about sequences and series, 1 over x squared, that this would be its graph, right? This would be its graph. So consider what we're trying to do here. We're trying to take 1 plus a fourth plus, what would be next? 9th plus 16. We're trying to add these up, right? Forever. And we're trying to figure out, does it converge or diverge? I'm going to start putting those on here. But I'm going to do it, man, this is a little too big. Let me see if I can make it a little bit smaller. Yeah, I'm going to do it in a way where I'm going to draw rectangles, where each of the bases of these rectangles is 1. Okay, and the height here is the value of the sequence. Remember, the sequence is just points, aren't they? Dots. But I'm creating a rectangle. This is 1 wide and how tall? 1. So that has an area of 1, doesn't it?
Yeah.
Okay, now I'm going to create another one. Oh, what did I do here? There's my second one. So it's 1 wide, and how tall is it? 1/4, right? 1/4. So what's the area of this one? 1/4. Okay. And now I keep going. Next one. That's going to be 1 wide and 1/9 high. Do you all see where I'm headed with this? What?
So we start at n equals 1. That first rectangle, wouldn't that be if you were to start at n equals 0?
No, I'm just showing you that there's a picture over here, right? This picture, this is 1 right here.
Yeah.
If I go up 1 and then draw a rectangle this way and down, that area of that rectangle, right? That area of that rectangle is definitely a 1. Yes?
Yeah.
And then if I go to 2 and go up and then over and down, the area of that's 1/4.
Yeah.
Yes? Keep doing this. Okay, keep doing this. What can you tell me about the area of all these rectangles? Well, I know they're getting smaller, but what can you tell me about the total area of all of these rectangles? How is it related to the area underneath the graph? Is it the same?
No. Or, well, actually,
Look at the red. Let me bring the red in. Let me look at the red here.
I guess if you're going out towards infinity, it's small.
Let me take the sequence out of here. This right here in reddish purple, whatever, that is the integral from 1 to infinity, right, of 1 over x squared dx. Do y'all agree that's what that is? Okay. Could we do that integral?
Yes.
Yes, and we actually learned how to do that already, and we know that that converges to a number. But now I'm asking you to consider this sequence, right, which is these rectangles here. And I'm asking you to compare this answer with the integral to the sum of the rectangles.
There's like a negative space there, I guess, on top of
Yeah.
each.
Ignore that rectangle for a moment, okay? Ignore that one. Tell me about this sum of all those rectangles. How is it related to the area of the red? It's less than. Do y'all agree? The area of the red is bigger than the area of those rectangles that you see over here, isn't it?
Yeah.
So what if I tell you that the area of the red converges? What are you going to tell me about the rectangles? They converge as well, right?
Yeah.
Okay. If the area of red is finite, then the area of those rectangles must be finite as well. But I have one more rectangle over here. Does that screw anything up? No, because that is finite as well, right? So if that red area is finite, then that's finite, and if you add one more thing to a finite number, it's still finite. So this integral test or the integral test, which is what this is about, basically allows us to not even talk about the sequence anymore. Instead, we go look at the integral. And if the integral converges, then so does the sequence. All right?
But we just don't know like the sum.
We won't know the sum. So when we started this section, very first thing I said is we can only find the sum of geometric and telescopic, right? That's it. If they converge, we can find the sum. Otherwise, it's all about does it converge or diverge. This integral test will tell us whether or not we converge or not, but it will not tell us what to.
So it's not, I'm not gonna say it's not particularly useful for telescopic and geometric, but like,
Is what's not particularly.
like the integral, like in other words, if you had to find the sum anyway, I mean, we
So it's hard to see the forest through the trees in this. It may not make sense right now to us why all we care about is convergence or divergence, but believe it or not, that is all we're going to need to know if we ever get to the next sections, all right? Because we have 6 days left. If we get to the next sections, because what that's going to actually turn into is that these series are actually going to turn into functions, right? These series are going to become functions. And whether or not it converges or diverges is going to be the domain of the function. So if it'll converge sometimes and not converge other times, and that dictates the domain of the function. And once you know the domain, then you know when that function is defined and when it's valid. And so it's hard to see that right now, because you're like, yeah, don't we want to know what it adds up to be? Like, yeah, I mean, this seems like who cares? It converges, but you can't tell me what to, right? So I understand it doesn't seem practical, but it actually is all we need for later. Okay, so if I draw it this way, then everyone's happy? Yes? All right, now I'm going to ask you, what about the other way around? What if I take 1 over x instead of 1 over x squared? Then that's this, right? Right, 1 over x, here's the picture.
isn't it asymptotic?
We're going from 1 to infinity, not 0 to infinity. So there's no asymptote over here because we're starting at 1 and going this way. Do you all remember whether or not this integral converges or diverges? It diverges. This diverges. This goes to infinity. As a sequence, we're doing this. Right? 1 over n is like 1 over x. Does that converge or diverge? You can tell me. You should be able to tell me on this one. What type of series is that?
Harmonic.
It's harmonic. Constant over linear. That's harmonic. That diverges. Notice this diverged and that diverged, right? Let me see if I can convince you of that visually. So the area under this is infinite. The area under this is infinite because of what we already studied in this class with improper integrals. That's an infinite area. Now I'm going to start drawing rectangles. But watch the way I draw them. My first rectangle, instead of going up and over to the left and down, I'm going to go up and to the right and down. So this is 1 wide. How tall is it? 1, right? So what's the area of this? 1. Okay, let's go to the next one. Okay, on the next one I go out, this is 1 wide still, right? And I plug that in here, and I went up and over. So that's the next number. 1 plus, this is a half, plus a third, plus a fourth, right? So now this one, I'm plugging in 2. 2 gets plugged into 1 over n. You get 1/2. So what's the area of this? 1/2. Next one? 1/3. And the next one, 1/4. Oh, I went too low. Hold on. I'm supposed to go up to here, over, down, up to here, over, down. And I keep doing that the whole way. Notice that my rectangles are bigger, right? There's like surplus, there's extra. So the sum of the rectangles is bigger than the sum of the red this time. And the sum of the red was what? infinity, right? So that means the sum of the rectangles must be infinite as well because they add up to be more than the red. So look, all of this is just like a geometric trying to convince you of the ultimate conclusion here, which is this. This is the ultimate conclusion of what the integral test is going to be. If we consider a function f which is continuous, draw it without picking up our pencil, positive, always above the x-axis, decreasing, going down, and then consider that function restricted to the sequence, then if the integral from 1 to infinity converges, then so does this series. If the integral from 1 to infinity diverges, then so does the series. Whatever the integral does, the series does. That's the integral test. How to use it. This is probably the most important note right here. How do we use the integral test? So we're given a series, right? We're asked, does it converge or diverge? First thing we do, we convert the series, the sequence formula, into a function of f, right? So we convert it to a function. Once we convert it, we need to show first that it's a continuous function. So it has to be continuous. We then have to show that it's positive. We need to show that it's always above the x-axis. Then we need to show it's decreasing. How do we show something is decreasing in Cal 1? I just covered this in my Cal 1 class today. How do we show something, a function is decreasing in Cal 1?
The derivative is negative.
The derivative has to be negative. If the derivative of a function is negative, you're going down. So when it comes to showing that the function is decreasing, we actually have two options. We can show that the derivative is negative, or we can use the definition of decreasing, which I'll show to you when we get to the actual example. There's two different options. I'll show you both ways. So once you've shown that it's continuous, positive, and decreasing, once you've shown those three things, then you evaluate the integral. Whatever the integral does, that's what your series does. Here we go. Does this series converge or diverge? You look at it. Start running your test. N-term test, pregnancy test. Let that n go to infinity. 1 over infinity goes to 0. Test fails. Is it geometric? Do you see n in an exponent? No, not geometric. Is it harmonic? Constant over square root of linear. That's not harmonic, right? It has to be constant over linear. So non-harmonic? Telescopic? I don't see any way that we could ever split it apart into anything where we're going to get things that start like canceling out. We would need a subtraction somewhere in there for that to happen. Like, yeah, I don't think it's not going to happen. So integral test is the only other thing we have, right? So what I'm going to do is I'm going to convert that sequence to a function. Let me go through the actual steps. I'm going to do them side by side here. Yeah, I'll do it right here. Make this a little smaller. So the sequence we're given here, all right, the one we're looking at is 1 over the square root of n plus 1, right? That's what we're looking at. All right, first I'm going to convert it to a function. So to do this step, we're going to write f of x equals 1 over the square root of x plus 1. That's a function, right? Show that it's continuous on the interval 1 to infinity. Is it continuous? Why?
Because you can always combine those numbers from 1 to infinity.
It's only discontinuities
It's only undefined.
I'm getting the same correct answer from. The only problem you have to worry about here is if this is what, -1? Or there's some other numbers. Basically, you need this. You need x plus 1 to be greater than 0, don't you?
Yes.
As long as this radicand is greater than 0, you're in business. And that just means that x has to be greater than -1. As long as x is greater than -1, then this thing is defined. Is x going to be greater than -1?
Yes.
Why?
Because it's from 1 to infinity.
Yeah, because we're going from 1 to infinity. So is it continuous? Yes. That's a visual inspection. All right, is it positive? Is this function positive on the interval 1 to infinity?
Yes.
Yes, because numerator is 1. 1 is always a positive number. And then what's underneath this radical is always positive, or else we can't do it, right? And the square root of a positive number is always positive. So this is definitely a positive function, meaning that it's always above the x-axis when we draw it. And then the fourth thing we have to show is the hardest, because this is going to depend on how you want to do it. But you have to show it. If you don't show this, you lose points, because you have to have these conditions for the test to even be applied. So is it decreasing? Well, to do that, I'm going to use option B. I'm going to look at the derivative. What's the derivative of that function? So this depends on you, how you would take that derivative. There's so many different ways to do it. Would you do a negative power? Would you do quotient rule? It all depends on you. Maybe we could do this. Rewrite this as x plus 1 to the negative 1/2 power. Isn't that the same thing? Isn't that the same? And then what's the derivative of that? You want to give me a derivative? You look like you need a little pep in here. Yeah? You want to give me a derivative? I'll try and get you engaged so you...
No, it's okay.
You're right?
Yeah, I'm right.
Derivative?
Negative 1/2 x plus 1 to the
Negative 1/2
3 halves.
x plus 1 to the negative 3 halves, right? That's power rule. Bringing down the half, negative half, that to the negative 3 halves, subtract 1, and then derivative of the inside, which is 1. Okay, so that's it, right? Is that always negative? That's what I'm trying to check. Is this always a negative number? You got to convince yourself and me that this is always negative. How about I do this? What is this 3? I'm dropping it down. What does 3 halves really mean? Square root cubed.
Yeah.
Is that always going to be negative? I mean, sorry. I did not mean to say that. What will that always be is what I should have said. This is always square root of x plus 1 cubed. Why is this always positive? Well, the square root will mess up. Can't it mess up if this is negative in here?
Yes.
But it's not going to be negative, will it?
1 to infinity.
Because it's 1 to infinity. We know that this will always be positive. Square root of a positive number is positive. Cubing a positive number is positive. 2 times a positive number is positive. And negative 1 divided by a positive number is always negative. This is always a negative number.
That's what
So this is a decreasing function. Okay? So I have met all the conditions I need to apply the integral test. I converted my sequence to a function. I showed that it was continuous. I showed that it's positive on the interval 1 infinity. I showed that it's decreasing on the interval 1 infinity. And now all I need to do is evaluate the integral. If I can evaluate the integral, whatever the integral does, that's what the series does. Yes?
Like on our final,
Yep.
for showing, like, proving that, like, the steps, the first 3, is that more of like a visual?
This is more visual. This is more computational.
Okay.
Okay? All right, let me do the integral. Yes?
So if it passes all these tests, we're like guaranteed to get an answer? Like, we don't
No, we still have to integrate it. I mean, you have to still be able to do the integral.
Yeah, but I mean, like,
If you can do it, then yes, you will have an answer.
Yeah, because like sometimes the end term doesn't give you, like, you have to go to another one.
Yeah, yes, I understand what you're saying. So as long as we can do this, this integral is either going to converge or diverge. If the integral converges, the series converges. If it diverges, it diverges. So now we do the integral. We're going from 1 to infinity. We're doing 1 over the square root of x plus 1 dx. That's the integral we're doing. What's our technique of integration here? Okay, so we're going to replace that infinity on top with a limit. Good. And then we have to find an antiderivative, don't we? What's the technique of integration here? Basic U sub. Basic U sub. No trig sub. Don't be saying trig sub. That's, if this were an x squared, then I'd be thinking trig sub. But because it's just x plus 1 down there, thinking basic U sub. Maybe we just do that over here. Let's do that. If I were trying to integrate this, I would do just a basic U sub is x plus 1. The derivative of that's dx. And then this just becomes 1 over the square root of u du. Right? It's a pretty straightforward u sub. This is u to the negative half du, and what's the antiderivative there?
It's,
Like u 2 over 3?
2,
oh, that's right.
2 root 2. I mean, sorry, 2 root u, not 2 root. 2 root u plus some constant. That's what that should be.
Oh, yes, yes.
And then replace u with x plus 1. So now we're here. Limit t goes to infinity. All right, the antiderivative, which we just found, was 2 square root of x plus 1, but we're evaluating that from 1 to t. Any questions? Limit t goes to infinity. All right, and now I plug in the two different values. So if I plug in t, I get 2 root t plus 1. If I plug in 1, I get 2 root 2. And now let t go to infinity, and what happens? That becomes infinite. That blows up. And that's just a number. So this goes to infinity, which means the integral does what? Diverges, which means the series diverges. So the integral diverges, which implies that the series diverges as well. Questions?
I
Yeah.
hope this isn't a dumb question. So infinity minus a number is still infinity, right? Because that's the logic there.
Yeah, yeah. Uh-huh. It's a finite number taken away from an infinitely big number. All right, let's look at this next one. All right, we start running through the different ideas here. First thing, run the n term test, right? Forget that. Let n go to infinity. What do we get? Infinity over infinity. L'Hopital, derivative top. 1, derivative bottom. It's going to go to, so it's going to 0. This fails, right? Nothing? Okay, is it geometric?
No.
Almost.
Well, almost.
Almost. Actually, if we would have had this, if I would have had this,